Good to be with you. I'm really pleased to have this opportunity to describe some of the slides in my last class with you to help you grasp the information. Thank you for submitting all of your homework. I've received homework from everybody, and I've started receiving some of the homework due on Monday. That is your paper topic, and well, let's just say a paper proposal. Thank you for that. I hope you're all staying safe. These are challenging times. I wish you all the best. So what I'd like to do here is just go over a few slides with you. Some of the first three slides in this presentation, slides you've seen, for example, this one that shows the global water cycle, which shows basically water evaporating from the ocean and then being transported by wind over land, where because of the high elevation of the water that is evaporated and moved up in the atmosphere, it cools, condenses, and precipitates as rain or snow, and then flows back into the ocean through rivers. Some of it infiltrates or percolates into the ground and becomes groundwater that is either released as springs into streams that flow into ponds, lakes, and then eventually to the ocean, or directly into the ocean as groundwater. So you've seen that basically we have three major water reservoirs: the atmosphere, with all the water in the atmosphere, and then you have surface water, which is all the rivers, ponds, lakes, the ocean, and then the other major reservoir is groundwater. This lecture is based on groundwater, and subsequent lectures will be on surface water. You also saw this slide, which I'm sorry, it had the wrong label. In fact, I'll submit another PowerPoint presentation. I believe in the presentation I submitted, it had some kind of a label. I don't remember what it says, but it is supposed to say, ask the question, how much fresh water is there? But it said, the other one said something like alleviation of disease or something. So sorry about that. But this is really aimed at making the point that we have a lot of water on Earth, but most of it is salt water. About 97.2% of all the water on Earth is salt water, which is not of too much use for us in terms of the fresh water that we need. And of the other 2.8, we end up with something like 0.6, that is groundwater we're going to talk about today. The rest of it is just locked up in either ice, glaciers, or in streams that flow, and also in plant and animal matter. So here we are. We're going to focus on groundwater, which is really 0.6% of the hydrosphere. That is all the waters that are available to us. We're going to take a deep dive into that. There are two terms I'd like for us to discuss first that will help you understand several lectures that will follow. And those are porosity and permeability. Consider porosity as the percentage of a rock or sediment that consists of void openings. That is, the space in a rock that is not occupied by the rock. So the pore spaces could be filled with air, could be filled with water, but that is what porosity is, the holes that are within a rock. And permeability is just the ability of fluid, of a substance to transmit fluid. Say a rock, for example. If you place water on the surface of a rock and it flows through it on the other side, we say that rock is permeable. So it allows water to flow through it. And if it is not permeable, we say it is impermeable. So it's either permeable or impermeable. So we're going to use that information to explain a few things that will follow. So porosity, which is the percent of void spaces in a rock, permeability, the ability of the rock to transmit fluid. Here is a diagram that further explains that. The picture to the left has high porosity. Think of, say, baseballs, no, not baseballs, golf balls put in a big bucket, and the gaps between them, these white spaces, are the pore spaces that are not the rock. And the percentage of how much of these pore spaces make up this rock is what is known as porosity. This rock has high porosity, as you can see, because there's a lot of open spaces. The diagram to the right, on the other hand, you can conduct this experiment as well. If you take golf balls, throw them in a bucket, and then you take marbles and throw them in that bucket, the marbles will fill the gaps between the golf balls. And so the total amount of pore spaces available will be smaller in the rock to the right as compared to the rock in the left. And if you threw those marbles, say like this, and then you took other smaller pieces of marble or pieces of rock and threw them in there, it will further occupy some of the spaces that are currently open, and that will further reduce porosity. And if you poured water on the surface of this rock on the left, it will just go straight down very easily. The rock on the right, it will go down, but it will be slower because the porosity is lower. So that's porosity. Here, let's talk about permeability, the ability of a rock to transmit fluid. If you look to the extreme left, you see that the rock has no air spaces. If you pour water at the top of the rock here, that water is not going to go to the bottom because this rock is non-porous. And because it cannot hold water, it cannot transmit water, we also say it's non-permeable or impermeable. If you go to the extreme right, you will see that the rock has a lot of pore spaces that are connected. If you pour water at the top, it will make its way all the way to the bottom. So this rock is porous, both porous and permeable. If you look in the middle here, however, you will see that the rock has pores, but those pores are not connected. And so while it has porosity, in other words, it has air spaces, if you place water at the top, that water is not going to flow all the way to the bottom, which means this rock is porous but non-permeable or impermeable. So that is the distinction between those two. If we take that knowledge now to the real world and look at these rock layers, just assume that at the bottom here, we have what we call an impermeable rock. So a rock in which if you put water, it doesn't flow to the bottom. And from this boundary here, all the way to the top, you have a permeable rock. What will happen is when it rains at the top here, the water will infiltrate or it will sink into the ground and go through the pore spaces until it gets to this rock layer where you have impermeable rock. And it will start filling up and building up in the pore spaces. Just like if you had poured water in that jar with that bucket with marbles, with golf balls, the water will fill from the bottom because the bottom of the flask itself is not permeable. So the water will fill the pore spaces up to a certain height, That height where the water ends is what is known as the water table. Okay, see it labeled here. And from this water table to this top, you just have porous rock that doesn't have water. If you have more rain, this water table will keep moving up. In some areas, the water table is so high that it comes all the way to the surface, and we call those areas wetlands or swamps or marshes. Okay? And if you drill the well here, you will get water because you've crossed the water table. If your well only ended here, then you're not going to have water in your well. We're going to talk more about wells shortly. So that is that. This diagram looks a bit messy and complicated, but it is not really that complicated when you take a close look at it. So it is a cross-section of the earth. So that is the surface there with rivers running, small rivers running into, draining into the big river, which then flows out of the page to the right there next to that house. Here you have a permeable rock. We do not see the impermeable rock, it's below this diagram. And so when it rains, water goes through the ground and all the way until it gets to an impermeable layer, which is below this diagram, and then fills up all the way to here. As you can see, this area that is blue below, that represents the water table, this line here. And this water table is not fixed. It fluctuates depending on seasons. During the rainy season, this water table can move all the way up here to this level. So this band you see here represents the fluctuation of the water table. It's here when the water table is lower. I mean when you have dry season or a drought, and here when it's wet. Just some terminology. This region above the water table, where water just goes through, is known as the unsaturated zone. And the area where you have water is known as the saturated zone. So the water table can be defined as the boundary between the saturated and unsaturated zone. Then this other area here that is that doesn't have water at all is what is known as the vadose zone. Here, where water just goes through, we'll see another diagram where that is better defined. The other thing here, again, another terminology, I've used this word before, infiltration, that is the process of water seeping into the ground. The other thing I wanted to note here is that you have two homes here, each of them with a well. As you can see, this house, this homeowner, he drilled his well all the way here, meaning this guy only has water when the water table rises, because the well is only up to the highest point of the water table. If you look at this home, on the other hand, has a very deep well all the way crossing the water table, which means no matter how low the water table goes for this region, he will always have water.